I'm going to be talking to you today about some use of biological information to actually develop water quality criteria and why we're doing that. Now, I know later in the day, if I see a talk late in the day, I can usually remember what color background the slides were or maybe what colored shirt the presenter had on, but my brain is so gone by then that I really don't remember much of the content. So I'm giving you the take-home message right up front. And that way, if you had a really starch-heavy, carbohydrate-y lunch and you just want to click it off, go ahead. And you'll see this at the end again, so we'll come back to it. But that is that criteria for a lot of water quality constituents do not really lend themselves to lab-based toxic approaches like we've loved to use for the last 30 years. And that field-based approaches are continuing to sort of surge in use and development. And the use of biological monitoring data has become really critical to that because it's this reservoir of data sitting out there waiting to be used. And that California is applying such approaches to nutrients. And that is really good news for field biologists. I do some work with EPA headquarters, and the nutrient branch and the biological branch are in the same group, are in the same branch at EPA. And in the 80s and 90s, you would go to a freshwater sciences meeting, and there'd be like 8 concurrent sessions on bioassessment, and biology was just booming. And then nutrients hit, and it was like biology went quiet for a while. People stopped giving talks about indicators, and they were starting to talk about nutrients. And funding was being pulled out of state bioassessment programs for monitoring and going into nutrient studies and stuff like that. And then everyone realized that really in order to do nutrient criteria, you needed biological response information. And all of a sudden, they're just in love with biology again. So this is really good news for biologists, I think, if you're a biologist. So for those of you who aren't aware of the evolution of assessment, original indices for bioassessment, when the Germans invented them in the 1800s, like they invented everything, were single metric, sort of tolerance-based indices, like the HBI, the Hilsenhoff Biological Index. And then the second generation indices were really multi-metric and assemblage-based. You had the whole multi-metric index movement, and then the OVRE models came out of England, and percent model affinity, the folks in New York were playing with their sort of unique approach to it. But there's a lot of information sort of stored in taxonomic presence, the presence of individual taxa and the absence of certain taxa and the abundance of that information, which was really important in the development of those early indices. And I think we're starting to realize the importance of that information and looking at individual stressors and how we might construct criteria to protect streams from the adverse effect of those. And so after this sort of period of bioassessment and develop a more sophisticated indices, we started getting into causal assessment and the rise of causal assessment. Like stressor identification and the CADIS products that EPA have put out, and that really spurred disentanglement of biological indices, of putting everything together and coming up with one number. Instead, digging back into the individual taxa, getting very specific about which taxa are disappearing, and using that to try and infer what might be going on chemically or physically in the environment that's causing this biological impairment. And we were after these questions of why is a site impaired, what's the cause of that impairment, and can the taxa tell you what's going on? And we got into these complex multivariate statistical techniques to try and identify these gradients that were associated with certain taxa. We got into developing tolerance models again like they had done in the 1800s. We're doing again with more sophisticated math that does the same exact thing that it used to do, like developing these optima or weighted average models. And I think we so badly wanted there to be like taxonomic fingerprints for individual stressors so that you could go out to a site and you knew if you saw this pattern of bugs, it only meant it could be one stressor. And then we started doing CADIS, and someone mentioned that it's a difficult process, and you go through that difficult process and you spend weeks at it, and at the end you come up with this laundry list of stressors that you knew probably was there anyways. So we would really hoped that we would have more specific information. And at the same time, EPA started playing with field-based criteria development. And there were 2 concurrent efforts that went on. The first one was the development of this field-based benchmark for conductivity in central Appalachian streams. I don't know how many people have been following this, but this was developing a microsiemens per centimeter target of 300 microsiemens per centimeter that had an adverse impact on aquatic macroinvertebrates that was derived strictly from field-based data. So it was not a laboratory toxicity-based conductivity measure. This report was vetted. It went through, peer review, science advisory board review, and came out. And it was based on using a lot of these single taxon-based approaches. So deriving optima for different macroinvertebrate taxa for conductivity, and then using this species sensitivity distribution curves to identify, at what concentrations do you have the fewest taxa being impacted by conductivity. And so this is one of the first real times you see this field-based use of data. And at the same time that was going on, you had EPA came out with this stress response relationships document for developing numeric nutrient criteria, where you again are using field-based or what we call found data, and looking at gradients between nutrients and biological endpoints measured in the field, whether that's taxa of diatoms, taxa of macroinvertebrates, or chlorophyll A, either in the water column or in the bottom of the stream. And you're developing relationships based on those field-derived data to come up with numeric thresholds that you're going to either use for criteria development or TMDL setting or what have you. And so this is kind of a state change in sort of thinking about how you can derive criteria from one that almost always had to be done in the laboratory to one that might almost have to be done only in the field, because these types of stressors don't lend themselves to laboratory tests as well. So here are some sample applications that we've been involved with. Here's some data from the state of Mississippi. There's a couple slides here from Mississippi where we've looked at relationships between nutrients and macroinvertebrates there, because they didn't have algae data. A lot of states actually don't sample algae. Almost every state in the United States has a macroinvertebrate monitoring program. In fact, I think the map is completely filled out. I don't think there's a state left now that doesn't collect macroinvertebrates on some scale. But far, far fewer collect algae. You guys are lucky. Mississippi is one of those states that doesn't. So in terms of looking for a response measure to use, we were sort of stuck with macroinvertebrates. And these relationships are often really quite noisy. Mississippi is kind of unique, actually, in that these relationships are pretty good. Usually it's just a shotgun blast. But here we have total nitrogen and total phosphorus, and this is their CSCI. They call it the MBISC, the Mississippi Biological In-Stream Quality Measurement. I can't remember what it's called. And here in the western bioregion, they don't do a continuous prediction model like the OVRE, although I've been begging them to let me develop one for them. But they use still this MMI that they're using. So, and there in their west bioregion, they have this, what appeared to be a linear approach. So we used a linear interpolation model. And we solved for different endpoints based on their existing numeric value they use for deciding impairment there, what nutrient concentrations were associated with that. And that went in as a line of evidence for developing and exploring numeric criteria development. We also converted these values into probability relationships. So this is the probability of not meeting their biological target as a function of nutrient concentration. These curves do a better job of sort of communicating the risk in a regulatory sense of not meeting a biological goal in terms of nutrient enrichment. So we converted those, and this is that west bioregion again. In the southeast bioregion, it looked like they had more of a split, a change point associated with it. So instead of using a linear model, we settled on this split point regression model. And we could also convert that into an impairment probability again, and this is as a function of total phosphorus. And again, we're using their MBISC score, their MMI here, to come up with those numbers. And then there's some, there's a split point chooses the best point that results in two of the most different curves. And there's some error around that, so you can iterate that and get error around where that change point is occurring. And so we've been using these approaches in Mississippi. Where you do have algal data, you you have the opportunity to use periphyton response indicators. This is some work we have going on in the state of Oregon through the NSTEPS program, through the EPA Nutrient Scientific Technical Exchange Partnership and Support System. We've been looking at periphyton metrics in Oregon as a function of nutrients. So here you have this nutrient MMI and algal MMI that's been developed as a function of TP and TN, showing really good response. Excuse me, and what we've used there is these blue lines are the reference site. These are deciles or quartiles of the reference population. So this is the 75th percentile of reference and 90th percentile of reference, and then you can use this linear relationship between these between the nutrients and the algal MMI and come up with a nutrient concentration that's associated with that reference condition. And we're not just doing this in streams. We're using these same field-based techniques to come up with relationships for lakes as well, using a variety of endpoints. In this case, this is data from Tennessee and Wisconsin that as part of a project we're doing for the Office of Research and Development at EPA, where we're trying to develop downstream protective values for a watershed. You know, a lot of the relationships for streams get really noisy. The relationship between chlorophyll and nutrients in lake is really nice. Those Vollenweider curves are really pretty. I refer to that as lake envy. Stream people have lake envy because they have these really nice relationships. And so where you do have those nice relationships, is there a way to set a number for the just contributing watershed, for the streams in the contributing watershed, to try and prevent that downstream lake from violating its use? But some of the other endpoints we've been exploring in lakes, other than chlorophyll, is dissolved oxygen, because there's an existing standard for dissolved oxygen in lakes. And so we've been looking at relationships between chlorophyll and the probability of having a hypoxic hypolimnia, which, you know, it's really important to have oxygen in the bottom of the lake, especially for many fish species. So we've been modeling that using field data, and this is sort of an approach that Lester Yuan at EPA has sort of developed and explored with the National Lakes Assessment Data Set, and we sort of stole his idea and have been using it in Tennessee and Wisconsin and finding many of the same relationships. So not surprisingly, as you add chlorophyll to a lake, you suck oxygen out of the bottom of the lake. And we've been using these relationships to sort of guide the development of a chlorophyll A target. Because once you have a chlorophyll A target, because of those nice, you know, lake envy curves, once you have a nice chlorophyll target, you can solve for phosphorus and nitrogen. But it's getting to the chlorophyll target that's sometimes problematic. A lot of people just said, well, we'll use the trophic state index. Well, what does a trophic state index mean? It's just something Carlson came up with. It's a continuous way of standardizing chlorophyll, Secchi, and total phosphorus measurements. But it doesn't mean anything necessarily in a regulatory sense. You have to have a reason why you want a TSI value of 60. And the reason you may want a TSI value of 60 is because above 60, the dissolved oxygen disappears from the bottom of your lake. And now you have a linkage to a beneficial use target. So we've been doing that as well. And that brings me to this point, is that the response target that you're using, that value on the y-axis must link to some valued condition. That's really important, because ecological change is not necessarily sufficient. We would love managers to be concerned about any ecological change, but they have to answer to higher powers. And so we often have to communicate what that ecological change means in terms of beneficial uses. Like, this is a departure from reference. You know, we're starting to get away from what we expect the natural condition to be. If I look at your narrative standard, and your narrative standard says, as naturally occurs, at this value of an MMI or a CSCI, you're starting to move out of what is as naturally occurs. That's something that managers can understand because it's linked to the existing standard. So you can link it to reference, or you can link it to existing regulatory standards. You can say, well, at that chlorophyll concentration, you have a high propensity of violating your existing dissolved oxygen standard. They'll understand that. Now you've got an anchor to get a chlorophyll number and stick it into that really pretty lake curve. Damn lake people. So, you know, in the case of Mississippi, or this is Tennessee. Is that Tennessee? Yeah, Mississippi. we've developed these curves of what's the probability of violating the state in-lake dissolved oxygen standard as a function of chlorophyll and nutrients. And so this is allowing us to derive a chlorophyll value and defend it as the value that will protect their existing DO regulation. And then we link it to other things like fish, and lo and behold, not surprisingly, the same numbers kind of protects fish, because if you're protecting oxygen, you're protecting fish. And in the case of Oregon, we derived those targets on the y-axis based on the reference conditions. So once you sort of move out of here, above these values, you're starting to get into a periphyton score that is unlike what you would find in reference. So the reference zone is down here. This is an indicator that increases with disturbance. Sorry, I should have explained that. So having that linkage to a valued condition is important. So what we've been doing in California, most of you hopefully by now are familiar with this report that Betty and others put together and came out last year, was a monstrous analysis of the state algal monitoring data set, looking at relationships between a lot of these algal endpoints and chlorophyll and ash-free dry mass, but also periphyton measures and nutrients. And they conducted a number of sort of classical ecological change statistics, so change point analysis and Bayesian cart analysis, and looking at what is the structure of the relationship between these ecological endpoints and nutrients, and identifying these kinds of change points, which leads to the question, well, how do these change points relate to a designated or beneficial use goal? So she found a lot of what she calls, which I think is a really cool term, these exhaustion change points, where you're getting the sort of this decline, and then there's a change point, a statistical change point, which is a deadline. It's like, I wouldn't want to be, if this is my heart reading, I wouldn't want the doctor to be waiting till I flatlined, saying, hey, there's a change point right there. We should probably do something. So and this is a macroinvertebrate response, and this is chlorophyll here. And so you have to ask yourself, like, that's an ecological change point, a statistical change point, but is it a beneficial use goal change point? And so because California hasn't yet set or defined what these specific numeric goals are yet, the question became, well, if that is a value for chlorophyll you want to protect, what is the context for that? Is this value below where you really want biological conditions to be, or is it pretty, right on? And some of the common biological goal-setting approaches, which you're probably familiar with, are using some statistical property of a least disturbed reference population. And then there's this newer approach using expert elicitation based on the biological condition gradient. The biological condition gradient was a concept developed by a number of ecologists and staff at EPA to come up with a way of characterizing what is the phased, what are the phases with which a natural system falls apart? Okay, what are the ecological characteristics that change as you increase the pressure and stress on an ecosystem? And so they came up with, minimal loss of species, some density changes, some replacement of sensitive rare species. Some sensitive species are maintained, functions are largely maintained, tolerance is starting to increase in dominance. And these were tested and based and defended with literature and existing data. And they came up with this gradient that characterizes in narrative terms how things happen. And so you can actually train a model like this, and we'll talk about that in a second. But we took what Betty had done with the change point analysis, and we said, okay, let's at least use this old-fashioned way of defining what a biological goal is, which is using reference-based conditions. And it's been used for a long time. Most states rely on some percentage of reference to set their numeric targets, what you guys call bioobjectives and everybody else calls biocriteria. Most people use some percentile of reference to do that. And there is a linkage to narrative in Clean Water Act goals because integrity, biological integrity, which is in the Clean Water Act, is defined as sort of similar to natural, or similar to least disturbed conditions. So there's a path to get there. And so what we did is we identified all these response metrics like the EPT index or all the diatom indexes she used, and calculated reference percentiles of that, the 5th, the 10th, and the 25th or the 95th, 75th, and 85th if you're going the other direction. And built simple linear regression models relating nutrients or chlorophyll to these response measures. And we're solving for the X value, X-axis value, if it's chlorophyll or nutrients or what have you, that relates to that reference-based target. And we did that for all the metrics they had. And then we compared it to what the ecological change point values, just any change, were. And what these graphs show is basically these are cumulative distribution functions of all the reference-based endpoints. So if you look at the full range of metrics, and here we have, these are the invertebrate metrics, right, against chlorophyll, nitrogen, and phosphorus. The blue box is the range of the ecological change points that Betty and her colleagues developed for using just ecological change. And so the most sensitive reference-based values are here, down on this end. Look how nervous I am. And then the really high reference-based endpoints are up in the upper end. And so you can see sort of the meat of the distribution of what is in this case the chlorophyll concentration. What's the chlorophyll concentration associated with a reference percentile? Most of those are in the same range that you get using just ecological change point analysis. There are some that are on the low end, and there are some that are above it. But the meat of that distribution, 60 to 70% of the values lie in that same range. Does this make the decision any easier for regulators? Maybe not, because a regulator still needs to decide, am I going to pick a value below which half of my metrics are falling apart, are going beyond the reference condition? Or do you pick the most sensitive metric out there? Like if that's outside the reference, we're going to pick this value right here because that's when you get out of reference. Well, there's a lot of noise. So there's still some work to be done to figure out how you even interpret such a broad range of responses. Wisconsin was doing a similar thing, and they said, we'll just pick the average. And I'd explain to them, you know that half of your metrics are going outside of reference before you get there. Oh, well, we'll pick the lowest one. Well, you know that there's a lot of uncertainty associated with that. It might just be noise. What should we do? I don't know, pick the 25th percent. Algal models, the same sort of thing, right? So here's phosphorus and nitrogen. Here's the range from the ecological change points, and here's the range. Here's the distribution of values based on linking it to a reference percentile, so moving outside of reference. A little tighter for TN. But again, with phosphorus, you're talking about, about 50 to 60% of the reference-based endpoints in the same place as the ecological ones. So what's the next step with this? The next step in California is to do some biological condition gradient modeling. So we push the sort of traditional model of let's just pick reference-based numbers, and we'll use that as a guesstimate of where a management goal would be, because that's what everyone has always used. Well, let's try and link it to something more based on our knowledge of what falls apart as you add stress to a system using this biological condition gradient. So the next phase of the work, which we're doing along with the folks at SWRCB, which I spelled wrong again. Every time I spell SWRCB, I spell it wrong. At least I didn't put SQUIRP. EPA Region 9 and the State Water Board, we're going to be convening expert panels for invertebrates and algae, and we're going to be training a biological condition gradient model, and I'll explain how that does. It uses an expert elicitation process. So you get experts into a room, and you give them a list of taxa from a site, and they may not know anything else about that site. You don't give them physical chemistry. You don't give them physical characteristics at all. You might tell them what region of the state it came from so they can put themselves in expectation space. But then you just sort of ask them, looking at this list of taxa, what do you think, what characteristics along this narrative does that taxa list and its abundance, thank you, represent? Have there been some loss of sensitive rare species? Are you not seeing the sensitive rare species that you expect for that region here? Are tolerant species starting to increase in dominance? And so what happens when you train a BCG model is the experts actually slot a site into one of these 6 classes, if you use a 6-class model. And you get a lot of experts doing that for a lot of sites over and over again, and you get this fairly robust model that develops as a result of that. It's a little uncanny. We've done BCG models for EPA in over 15 states now, and we're doing them for coral reefs now and wetlands, and it's surprising how often this model works. And then you can get independent experts to do it again, and you plot them against each other, and they're fairly robust. You get high agreement between those. And so we're going to be training that model. And what can you do with the data once they're slotted? Well, some people actually develop a BCG model instead of an MMI or a CSCI or an OVRE model. They develop a biological cognition gradient model. And you can actually use the rules that experts are using as they go through a taxa list, and you can use it to, you can build a discriminant model or a predictive model that takes those decisions based in metric terms or in taxonomic terms and train a model that in the future you just put in a taxa list and it will spit out one of the 6 tiers that that site belongs in based on the expert models. That's in fact what the state of Maine uses for a bioassessment tool. They have a BCG model that's operationalized. But the other thing you can do with it is you can ground truth or crosswalk it to the values from reference sites or from the ecological change model. So for every site you have a BCG score, so your experts have put it into one of those tiers. And for those same sites, you also have a diatom index score, the H2O, H20. Damn it, I always forget that. The H20 model, I so want to call it H2O. The H20 model, and now you have some relationship between BCG tiers and the H20. And now you can say, okay, well here was the threshold from piecewise regression, or here was the threshold from the Bayesian card analysis, or here was the threshold from change point analysis that emerged from the H20 relative to nutrients. And here's where it tracks in terms of BCG space. It's on the 3-4 tier boundary. So it's where you're starting to lose some of your sensitive taxa and get an increase. Is that an acceptable ecological space in beneficial use terms to be at? What you don't want to see is like the endpoints you're deriving from nutrients to be like on the 6th boundary, right? Where, okay, these are the ones we think will protect uses, and really all they're protecting is like the worst condition you could possibly find. But we can also look at the reference-based derived values and say, okay, well, where are those? The ones when we developed the 75th or 85th percentile of reference, how do those values track on this BCG space? Is it where we're starting to get substantial changes in the ecological community? Is that an ecological condition that we really want to try and avoid? And so we'll be able to model that once we have these BCG tier scores from the experts. We'll be able to model those as a function of the same relationships that were developed from the 2 previous studies and crosswalk those to each other. So using biointegrity derived criteria, this will be completely obvious to most of you. You want a standard high-quality biological sampling program. You want paired stressor and response data to build models of those. They needn't be statistically complex. In fact, in EPA's stress response guidance, they went out of their way to recommend a very simple linear regression-based approach to doing this. Mostly because they felt it didn't need much more, but also because those types of models are very easy to explain to the public. Structural equation modeling, a little harder to explain to average people. Bayesian card analysis, you need like a keg of beer to explain that to a room of people. And they better have drunk it before you start. Classification integration, you can do this explicitly, like you build a separate model for each for the mountain class, or it can be done implicitly within the analysis itself. The response really needs to be anchored to a regulatory management goal. It's not enough all the times to do just, this is ecological change. That ecological change has to be put into the context of the ecological change that the regulatory management agency really is concerned about. So thank you very much.